Alright, here we're going to go and take a double replacement reaction and go all the way through all the steps. The first thing to a double replacement reaction is to predict products. Previous video gave you some examples on how to predict these. So stop the video right now and see if you can predict what's going to occur on the product side. Remember, you're going to bring one of each over when you switch the cations, and then you're going to check those charges and crisscross those charges down. So 1 to 1, check the charges. Stop it now to see if you can predict. Alright, so I'm going to take the Ag and hook it up with the PO4 because I've switched the cations. Na is going to hook up with NO3. I'm going to go ahead and now check those charges. Phosphate is a -3. Remember, our charges for transition metals come from what they were as a reactant. We know that nitrate was a -1. That means silver had to be a +1. So when I crisscross those charges down, it will be Ag3PO4. That's a 3 up there. When I write the actual formula, sorry that might look a little messy on the thing, I no longer have the charges showing. The charges is just there so that I can crisscross them to write a balanced compound. Alright, let's take a look over at this other product. I have a sodium, which has a +1 charge, and a nitrate that's a -1 charge, my infamous polyatomic. That's already written as a balanced compound, so I don't have to cross anything. Now this is not a double replacement reaction until one of the products actually makes a solid. Using your solubility rules in the back inside of your textbook, I always go to rule number 2, which states anything that has a sodium, potassium, or ammonium ion automatically makes it soluble. And luckily for us, this has a sodium ion. If something is soluble, you list that as AQ. It means it really exists as ions in a liquid solution. Don't always assume that the other compound automatically makes a solid. You still need to go through the solubility rules to determine if it does. Again, silver phosphate does not cover that rule number 2, which is your first rule you should always do when you're doing solubilities. That means then I have to look at the anion of this compound. I have to look under the solubility rules for phosphate. And if I read phosphate, it says that all the compounds are insoluble. It means then this would be the compound that makes a solid. Therefore, this is a double replacement reaction. I can then go on and write complete and net ionic equations. So remember, the first step is to switch those cations, bring one over each on this side, and then check the charges. Determine if there's a solid that is formed based on solubility rules. And the next part, in order for me to go on and do the complete ionic, is I need to balance the entire equation. This is where you're going to get the same number of sodiums on each side, the same phosphates on each side. Alright? So when we're balancing, I'm going to start with the sodium. I notice that that is one that's not balanced. I have 3 on this side and only 1 on this side. So to get 3 on both sides, I'm going to write a 3 in front of that compound. That then gives me 3 sodiums on each side. But because I wrote the 3 here, it does impact the nitrate ion. It says I have 3 nitrate ions. I have to go back over to this side and put a 3 in front of this compound so the nitrate's balanced. But again, as soon as I put a number in front of a compound, it impacts everything that's in that compound, so I need to recount. So in this one, I have 3 silvers, and if I go to the product side, I also have 3 silvers. Some students like to then, once it's balanced, write a number in front of each of compounds, even if it's a 1. Alright, because remember, when you're counting, you always go to that coefficient in front, and then you multiply it by the subscript when you're trying to do the counting part. Alright, so now that I know I've made a solid, I can write my complete ionic equations. These can look rather long and daunting I should say, but they're nothing more than counting atoms, which you just had to do to balance the equation at the top. Anything that is aqueous, you're going to divide into ions because it shows what those compounds are existing on a molecular level. And anything that's a solid, you're going to leave it as a solid because they don't make ions. So I'm going to break up sodium phosphate, that's an aqueous compound, into ions to help write the complete ionic equation. I'm always going to go to the number in front of my balanced equation and then multiply it by the subscript. So I have 3 sodium ions. I go back to that 1 and multiply by how many phosphates I have. So I have 1 phosphate. Notice I'm writing charges here because a complete ionic is going to show all the aqueous as ions. I'm going to continue on and make the silver nitrate into ions. I go to that front number of 3, multiply it by the denominator by silver, which is a +1. I'm sorry, it was a 1. Its charge is a +1. I'm going to go to the nitrate, go to the front, multiply by how many nitrates I have. There's 3 nitrates. All right, those are my reactant side being pulled apart. On my product side, I'm going to come down a little bit because I'm running out of room here. I make sure I leave the solid together. As I said, it doesn't break apart as ions, so make sure you do that. I'm going to break apart the 3 in front of the sodium nitrate. Remember, I go to the front, multiply it by the denominator. So there's 3 sodium ions, and I go back to that 3. There's 3 nitrate ions on here. That is the complete ionic equation. All right. Now, to get to the net ionic from the complete, what the net ionic is about is saying I'm only interested in the ions that actually make up the solid. The rest of these ions are spectators. They're watching what's happening. Anything that's on the opposite side of the arrow can be eliminated. So I notice I have 3 sodium ions over here. I have 3 on that side. On opposite sides of that arrow, I can cross it out. 3 nitrates, 3 nitrates, and they should match exactly. Anything that I have not cut out are ions that I can bring down here, and hopefully it will tie into all the ions that make the solid. It's like a checkpoint, and it does. Those ions represent that's in the solid. So you have your double replacement, your complete ionic, and your net ionic equation for this reaction.